Welcome to this lecture, and today we will start with our discussions on the teaching learning process related to a very important topic in fluid mechanics, the kinematics of flow. So, the question is, what is kinematics and why it is important, and why this should be one of the initial chapters in the discussion of fluid mechanics. So, kinematics talks about motion and not about the forces which are behind the motion. So, that does not mean that forces are not acting, but what it essentially means is that we leave the issue of forces on one side and we give importance to the motion which is maybe a consequence of various forces. So, this abstract understanding of motion is important because when we develop the laws of motion, there is a relationship between the cause and the effect. So, if you imagine the Newton's second law of motion, so you write force is related to acceleration and acceleration is a kinematic parameter. So, if we know how to write the kinematic parameters, we can write the expressions of forcing parameters by relating that with the kinematic parameters through a cause effect kind of a relationship. Again, in terms of teaching learning, when we were students, one of the earlier topics which were covered in the class was fluid statics, and this is not what I believe is compulsorily required to teach before fluid kinematics. The reason is that fluid statics primarily discusses about forces on a fluid when the fluid is at rest. So, that is not a necessary prior information before we study kinematics. So, that was more of a custom rather than a requirement. So, we will start with something which I believe is a requirement, that is to understand the motion, because although we say fluid mechanics which includes fluid statics, a major part of fluid mechanics is fluid dynamics, not the statics, and there the kinematics plays a very big role. So, what we are going to teach in kinematics, I will identify those items as pointers one after the other. So, description of fluid motion. Then concept of steady, unsteady or uniform, non-uniform flow, or basically and uniform, non-uniform flow. Streamline, streak line and path line. Then acceleration of flow. And then deformation, linear, volumetric, angular, and finally we will discuss about two important parametric representations, stream function and velocity potential. And we will bring a perspective of kinematics to all this. Why it is required? Description of fluid motion is required because fluid, unlike solid, is not very simple to describe. The reason is that the fluid is, when it is under motion, it is continuously deforming. So, for a solid, if you identify a fluid, if you identify a particle, it may be quite trivial to track the particle. For a fluid, it may not be that trivial to track the particle, and the reason is that the fluid presents a continuously deformable medium. So, if you could track individual particles, the description of fluid motion could have been the Lagrangian description. What is the Lagrangian description? Again, this description originates from the name of the famous mathematician Lagrange, who contributed towards the basic mathematical foundations of this subject. So, in the Lagrangian description, the position vector r of a particle is a function of the initial position vector and the time t, right. So, you are tracking the particle, it is now here, then here, then here, then here, in this way. If you make a locus of the particle, that is the Lagrangian approach. It is very difficult to do it for fluids, but not that people do not do it for fluids. There are certain cases when Lagrangian tracking of particles gives certain very special information. For example, how good mixing is in a fluid. So, it is not that Lagrangian approach is totally discarded, but it is not a very common thing for fluid. So, for fluids, the alternative approach is commonly used, that is the Eulerian approach. In the Eulerian approach, what we do, instead of fixing our attention on a particle, we fix our attention to a position or a location. So, what we do is that we consider an imaginary box, which is a location where we say focus our attention. Say you are sitting with a camera, so you focus your attention here and study what is happening across this. So, some fluid is coming in and some fluid is going out. Incidentally, this is called as a control volume, and this is not a bad way to introduce the concept of control volume to students, that it is a fixed region. The fixed region means specified region, that region itself may be moving. So, it is a specified region across which you have transport of whatever mass, momentum, energy, everything, but the region is specified. Lagrangian is the mass is specified. So, sometimes this is also called as a control mass approach, and this is also called as a control volume approach. So, here you are not bothering about where from the particle has come and where it will go. You are simply bothered about what is happening across this, and the change that is happening across this is culminated in the form of a velocity vector v or u, whatever you call, maybe we call it capital V, which is the function of the position at which the velocity is described and the time t, right. So, v is a function of, so see it is not a function of r0 anymore, right. We do not care where from the particle has come and where it will go, we are only bothered about what is there at that location where you are focusing your camera on. So, this much of information all of us provide in the class. What most of us miss is the connection between the Lagrangian and the Eulerian approach. So, where is the connectivity? The connectivity comes through this following definition: velocity of flow at a point is the velocity of a fluid particle located at that point at that instant of time. So, if we want to find out what is the velocity at this point, so how we can imagine what we can do? We can put a imaginary particle which has the same density as that of the fluid. This is called as a neutrally buoyant particle. So, when we have such a neutrally buoyant particle, then the velocity of this particle, whatever is its velocity, the same velocity is assigned as the velocity of flow at that point. So, the Lagrangian description of a particle at a point is essentially giving rise to the Eulerian description, provided the density of the particle and the density of the fluid are the same. Okay. So, now with this little bit of background, next concept is concept of steady, unsteady or uniform, non-uniform flow. So, I will not write the definition in the board because this is again I am iterating that it is not a regular class. So, my objective will be to brush up whatever we already know or whatever is information is already available. So, steady flow means what? So, when we say steady or unsteady, we are thinking of variation with time. When you are thinking of variation with time, you are fixing the position, because you cannot simultaneously imagine a variation with respect to time and variation with respect to position. You fix one and think about the change with respect to the other. So, steady means that at a given location, if you find that there is a change in fluid property, any fluid property, density, viscosity, surface tension, whatever, some fluid property and flow velocity, if these are not changing with time at a given point, then we say that the flow is steady, and otherwise it is unsteady. While steadiness or unsteadiness talks about variation with respect to time, uniformity or non-uniformity talks about variation with respect to position. So, when we say uniform or non-uniform flow, what we are essentially talking about, that given a particular time, whether at a given time the velocity and fluid properties are same at all locations in the flow field. Flow field is, what is a flow field? Flow field is the region over which you have the influence of flow felt. So, field, field theory is a very generalized theory, and fluid mechanics is one of the branches of the so called application oriented domain of field theory. So, flow field is essentially evolving from the terminology field, and field is a region over which some influence is felt. So, uniform flow means over the flow field at a given time the velocity and property, they are all uniform, they are not varying from one location to the other. Non-uniform means it is varying with position. So, the question is that, so now again this much of information is always provided to students in the class, Again what is missing is the linkage between the two. For example, can you have a steady but non-uniform flow? This is obvious, like I mean from our practical experience we know that, say if you have a pipe, if you have a flow which is not varying with time, but still there will be a variation of velocity across the radial direction of the pipe. At the wall the velocity is 0 and at the center line it is maximum. So that means this is the most obvious manifestation of a practical situation where the flow is steady but non-uniform. But the other way around, can the flow be uniform but unsteady, right? This is a little bit of brain work that is necessary to answer this. So then you have to understand the concept very clearly. So uniform means what? The velocity vectors, in terms of velocity I am not talking about properties, just I am giving velocity as an example. So in terms of velocity, the velocity vectors are same at all the points at a given instant of time. This keyword is very important. So let us say that at all these locations the velocity along the right is 1 meter per second. Now let us say after 1 minute these become this 2 meter per second vector in the same direction or in whatever other direction also it may be, that is also uniform. So now at a given point the velocity has changed from 1 meter per second to 2 meter per second over a period of time. That means it is unsteady, but at a given time it is same everywhere, that means it is uniform. So this is an example of an unsteady but uniform velocity field. The other concept about steadiness or unsteadiness, which is again commonly missed in the class, is that there is nothing called as absolute steady or absolute unsteady. It depends on the reference frame from which you are looking into the flow. So to illustrate this, normally this is the example that I give in the class. So if you have, let us say there is a river and there is a boat which is moving on the river with a fixed velocity with respect to the river water. There is a bridge, so imagine that there is a bridge like this and the river below it. So somebody who is standing on the bridge is observing the flow of the river water. So first the water below the bridge is a standstill, then the boat comes, creates a disturbance in the water, and then the boat goes away, the disturbance again dies down. So to the observer who is standing on the bridge, the water flow will appear to be unsteady, because at a given location which is below the bridge the water velocity is changing with time. Again the same river water, the person who is sitting on the boat is moving with the boat itself, and with respect to the boat the river water velocity is not changing with time. So to that person the same river water is appearing to be steady. So the same river water flow to some observer who is there in a fixed reference frame, the bridge is acting like a fixed reference frame, is appearing to be steady, unsteady, whereas to an observer who is moving with a reference frame, not accelerating reference frame, a reference frame which is moving with a uniform velocity, the same flow appears to be steady. So this is a transformation from a stationary reference frame to a reference frame which is moving with uniform velocity, not accelerating. This transformation is called as Galilean transformation, and this Galilean transformation can convert a steady flow, an unsteady flow to a steady flow. Okay. So, you see that although the description of fluid motion, steadiness, unsteadiness, these are sort of trivial things which we think in kinematics, there are finer details which I believe are important to be discussed in the class, in addition to the basic concepts of basic definitions of these concepts. These are the additional things. So, we have figured out that how do you describe the flow velocity, and essentially the velocity can be a function of position and time. Now, the question is that if you are doing an experiment, flow velocity measurement is one particular attribute, but the remaining issue that remains to be addressed is that how do you just qualitatively visualize the flow, right. For example, if you have a power plant, you see that smoke is emitting out of the chimney, that can give you the nice vortex structure which is there at the top of the chimney. So, smoke emission can itself give a flow visualization for gases. Similarly, for any general fluid, there are some traditional ways of looking into flow visualization, and these flow visualizations are therefore considered to be described by certain imaginary lines in the flow field, and those lines are streamline, streak line and path line. Okay. So, this is a big motivation before again I am telling that instead of streamlines are defined as this, and that is how you can start, or you can give a motivation, right. I mean, why do you require to define a streamline at all? It gives a flow visualization. So, this simple statement before defining what is streamline I believe is important. So, what is a streamline? I am not writing in the board because of interest of time, but I am verbally telling in case you want to recapitulate it. So, streamlines are imaginary lines in the flow field such that tangent to those lines at a given point at a given instant of time represents the velocity vector at that point at that instant of time. See, location and time both are important, because we have seen that in the Eulerian description the location and time both factors come into picture, right. So, again this is a gap in giving definition. In most of the classes teachers will say streamlines are such lines that tangent to the streamline at a point defines the velocity vector, does not talk about at a given instant of time. So, now if you have a streamline like this, so you have 2 points which are sufficiently close in the streamline. Let us join this by a position vector dr. Also consider the velocity vector which is v. So, these points P1 and P2 they may be wherever on the streamline, but let us say that we fix up P1 and bring P2 very close to P1. When we bring P2 very close to P1, then what does P1 P2 become? It becomes a tangent. That is the definition of a tangent to the curve. It is a limiting case of a chord, when the points connecting the chord they come very close to each other. So, when it becomes, so I have written it dr, that means I am assuming that P1 and P2 are actually differentially close. Just for clarity in the picture I have drawn it like this, but it is not actually correct, because when they are very close to each other then this is a tangent. By definition the velocity is also a tangent to the streamline. So, actually they should be coincident lines. So, the correct diagram will be, you have P1 P2 and you have the velocity vector. So, dr and v. Okay. So, if they are along the same direction, you have dr cross v is equal to a null vector, because angle between the two vectors is 0. So, we can write this cross product in a determinant form. So, this means that okay. So, if you have a vector which is a null vector, all the components are individually 0, right, where I, j, k are unit vectors along x, y, z. I mean, it is needless to mention this in such a forum of advanced level, but still, I mean, for completeness I mention this. So, this is 0, this is 0 and this is 0, and a combination of this is dx by u is equal to dy by v is equal to dz by w. Well, this is the equation of the streamline. This u, v and w are what? The velocity vector is ui plus vj plus wk. U, v and w are the components of the velocity. This u, v and w are also functions of time in addition to position. So, you have to fix up the time and then integrate this to get the equation of the streamline. So, streamline is done. Streak line, it is a very interesting thing. What it is? It is the locus of all particles now which at some earlier instance of time, different instance of time, pass through a common point. So, just to give you an example, let us say there is a pipe and you inject a colored dye at this point by an injection syringe. Say you inject a blue colored dye called as thymol blue, which looks like ink. So, now you inject this thing and then what happens is you you will see after some time there is a colored line in the flow field. So, how does this color line evolve? Whatever particles which passed through this point earlier got colored by this colored dye, and wherever they are now, if they are joined, they will give this colored appearance. So, it is a locus of all particles which at some earlier instant of time, different instants of time, pass through a common point. So, it is very clear that it is not a streamline, and this is the line which actually we visualize in the flow. Normally there is a misconcept that in experiments what we visualize is a streamline. We fundamentally visualize this streak line, not the streamline, but sometimes this becomes identical to the streamline, and we will see later on that when it becomes like this. Finally, path line. What is a path line? Path line is the locus of an identified fluid particle. So, path line is essentially a Lagrangian description, nothing more than that. So, it is just a locus of an identified particle. So, when we define streamline, streak line and path line like this, the concept does not become clear if we do not work out a clear illustrative problem which distinguishes these three lines. And in the next lecture my agenda therefore will be two things. One is to complete this conceptual discussion of streamline, streak line and path line through a simple illustrative problem that discusses the difference or that elaborates the difference between these, and then going one step from velocity describe the acceleration of flow. So, that will be the agenda in the next lecture. Thank you very much.